this week's lesson, how my training as an Inventioneer altered Ethernet.
Welcome. It's great to have you all here with us. You know, behind every great scientist, there's, well, just about everyone, there's a significant other. That's the case for me. You know, I actually met my wife at the zoo. Some of you don't know this. Yeah, I took one look at her in that uniform and I knew she was a keeper. So, okay, someone will explain that to you later. But okay, well, today's lesson is exciting. We're going to get a lot deeper into Ethernet networking, and you're going to learn about how it has really changed and improved over time, and really changed how much information you have access to. But first, a little bit of science news. Researchers at Karolinska Institute in Sweden have developed a new gene therapy that is giving people who are deaf the ability to hear. This very interesting treatment that they came up with involves actually doing one injection into their ear, people who have this certain type of hearing deficiency, and they were able to, within a few months, be able to hear. So they've just done this in a very small treatment study, just 10 participants in this, but every single person that they tried it on had positive results. You know, with this treatment, it was ranging from age 1 up to age 24 that did this, and in some cases, people hearing for the first time, which was pretty exciting. So a lot of other really neat scientific breakthroughs that are changing a lot of people's lives coming your way. Well, without further ado, I get to introduce the host of Science Live, Dr. Roger Billings, along with co-host Paige Monet.
You didn't know I could do that, did you?
So I guess now I'm the co-host.
No, you're the man. You're the host.
Can you imagine what it would be like to go your whole life without hearing and then hear for the first time?
I was trying to imagine that.
Yeah.
It's got me emotional.
It's really quite exciting. You know, I like to think of myself and people like me as inventioneers. Mm-hmm. And inventioneers is kind of the intersection between science and engineering, but we look for problems in the world, and when we find a problem, then we try to study the problem to determine what is the cause and then to fix it.
Right.
And problem with gasoline engines is that they gave pollution. And so the hydrogen engine was to try and fix that. And you've gone through, that's been a lot of what my career has been about. And I think that for someone not to be able to hear, hearing is such a wonderful blessing. You can enjoy music and so many things. And to think that some Inventioneers were able to identify and understand exactly what the problem was. And once they could understand the problem, then they figured out a way to fix it. I think it's absolutely exciting. Well, today we're going to talk about Ethernet, only this time we're getting into the exciting half from my perspective. So I'd like to start out by introducing Tobias to give us some historical background.
All right, I'm a little bit nervous because I get to talk about this gentleman here. And we're going to talk about gigabit networking. Now, you know, we learned about how Ethernet was kind of the new way that computers connected together. Well, if you jump back into the early days of computing with these computers and computers getting more personal, we're talking like the 70s and going into the 80s and the 90s. You're in the 70s, Dr. Roger Billings has the Billings computer systems, and he's looking at how he can connect these computers he's made, and they're becoming so popular. And he has his other breakthrough that we're not going to talk too much about, of client-server computing, of instead of just connecting computers, what if you connected them to servers and then you had the server? So a network, right? And so as he starts realizing how much more we can now connect computers, which was his vision, he starts learning about this Ethernet networking because he wants to start connecting his computers. Well, as he starts looking at how to connect these computers, he runs into the issues of Ethernet at the time, okay? Now, Ethernet, of course, it was this great new way to be able to connect computers to each other so that they could send data to each other and do stuff, okay? But there was a problem. It was really, really slow. And it was, and so I'll throw out a number, it was 1 million megabits per second was the speed. Now that, whoa, I hear 1 million, but that's bits, okay, like ones and zeros. And so as far as computing goes, that's not very much per second, okay? And if you can take that and call 1 megabit per second, okay? So 1 megabit per second, and they tried to get that faster. Eventually they got it up to like 10 megabits per second. But that was like the top speed. And so when Dr. Billings looked at that and started seeing the systems that they were doing, he was pretty frustrated. He wanted it way faster. His vision for what we could do with computers and the kinds of data we could send, you would need a much faster network. And so he was pretty sure we needed one and that he could build one faster, okay? So now that's, a lot of us think, well, I can do that. But then you start getting into it and then you run into the problems, then you're like, never mind, right? So as he started getting into it and he started looking at how to make a network go faster, he started to learn about some of the issues that existed. And one of the big ones was, okay, you have this network of computers. They're connected with wires, and they're going to send data. So this computer sends out data, goes on the network. That's nice. This one sends data, goes on the network. It goes to like a hub where all the computers are connected to. But what if they send it at the same time? Then you have this collision. And if they send it at the exact same time and it collides, they try again, and it collides again. And you keep getting these collisions. And so the breakthrough that they had kind of put together was, okay, well, when they collide, we'll make a system that senses the collision and it offsets the sending of the two different computers. So if two computers send at the same time and they collide, then they'll sense there was a collision and they'll send at different times so that it won't collide. But when you start adding more computers and start sending more data, you still get so many collisions. If you get past like 70% saturation on the network, it just gets crazy to the point where it's super, super slow. And so the first issue he had to look at was collisions. And so he had this phenomenal idea. What if we got rid of collisions? And that might, yeah, of course, get rid of collisions. But actually, some specialists were like, well, you can't do that. I mean, that's like getting rid of the network. Because if you don't have collisions, how are you going to tell other computers are sending? Because they used collisions to start the offset timing. And yeah, what if we got rid of all the collisions? And so what he ended up doing was creating a system with a special chip, and Dr. John talked a little bit about this last week, the FIFO chip. Remember the FIFO chip, first in, first out. And it's kind of like, the mom at the amusement park who makes everyone get in line, okay? Get in line, get organized, you can go out when it's your turn, okay? And that's basically what this chip would do is all these computers are sending data and it's coming to this hub, and instead of it crashing or it turning into this garbled mess, it would take all of this data that's coming in, and if this one has arrived, it can go out. But if there's more coming in, they've got to wait their turn until it's their turn to go out. And so it would build up a memory, the buffering of this data, and then be sending it out. And so all of a sudden, you didn't have collisions because this chip could handle these coming in, and it would just send them out as in order and at different times. That seems so simple, but all of a sudden, he got rid of collisions on his product. And he named his product not a hub, but a concentrator. Okay? So as we start getting into, now the collisions are gone, how are you going to get up to high speed? Now, he didn't want to just go like 10 megabits per second or 20 megabits per second. Remember, 1 megabit per second is 1 million bits a second. He thought he could go 1,000 times faster. Big dreams. That's 1 billion bits a second, or what would become called 1 gigabit. So 1 gigabit, and that is 1 billion bits. How in the world could you make a network that fast? But if you could, think of what you could send. You could watch video over it, which sounded like never, right? And so we need to look at the cables that they were starting to use in Ethernet. By now, they were starting to use twisted pair cables. So here's a category 5 network cable, and you can see there's these twisted pairs inside. And so he starts looking at how he can send high-speed data at high speeds. But when he starts to send it, especially long distances, he starts to run into some major issues with voltages changing when it goes from this side to the other side. And I'm not going to get too deep into that because, whoa, it's deep. So, but basically, he figures out how to send data faster by equalizing the voltage of the various frequencies of data. And if you think that's deep, yeah, it's deep. But he gets gigabit speeds on his network. And so he starts a company, he calls it wideband networking, and he starts to sell products. This is in the early 90s. He's selling products where you could set up a computer Ethernet system, a network, and if you used wideband on the parts of your network, you could actually send and receive data at these gigabit speeds, okay? Now, in the mid-90s, the IEEE is going to have a meeting. Now, this is the Institute of Electrical and Electronics Engineers. They're going to have a meeting to decide networking standards. And so Dr. Billings is a member, and he's at these meetings where we're going to put together the standard. And no, that'd be great, because then it wouldn't just be, it would be something that could be used all over the place, and we could enjoy these speeds everywhere. So hopefully we can get these inventions incorporated, right? Well, they start having their meeting. He comes to the committee meeting where we're going to meet together and we're going to decide the standards. There's over 1,000 people in the meeting, and it's like a conference. And he shares his idea and what he's been selling already for years of, it's a system that has no collisions, and I'm getting gigabit speeds. And some of the engineers are like, that's impossible. Like, you can't, no. You can't send data at gigabit speeds over copper. Like, that's impossible. Like, you must be telling stories, because that's not possible. And they voted to not even go that way. We're not going to listen to his proposal. We're going to do something different. And so then they put together another idea, and they actually voted on it, and they accepted it. And it was basically, okay, so you know that wire that had the 4 pairs of wire? We're going to send our data down those 4 pairs of wire, but we're going to cut it into fourths. And we'll send 1/4 of the data down each pair at 1/4 of the gigabit speed, and then we'll put it back together on the other side, because you can't send gigabit speeds over copper. And that's how we'll get around it. We'll send it 1/4, 1/4, 1/4, 1/4, and we'll bring them all back together on the other side. Win. And so that is what they voted on. And they said, that's what we're doing. We're sending it this way on the 4 pairs, breaking it out into fourths, and it's coming in on the other side. But there was one issue, okay? The issue was, well, we've reached gigabit speeds for sending our data, but you got to send and you have to receive. What about this side when they're sending data back? Well, it's easy. We'll take turns, right? Like walkie-talkies, because we can't send and receive at the same time. Because if this side sends and this side sends, we already know about collisions. So to avoid collisions, this side will send, then this side will send, then this side will send, like walkie-talkies. You got to take turns. But the problem is, that's what engineers call half duplex, because you can't go full gigabit speeds, even if you're sending at gigabit speeds, if you have to wait for half the time to have a turn. So it's gigabit speeds, but it's not, is basically what this was. And so Dr. Billings was like, well, that's a really bad idea. Can't we send at the same time? And they were like, well, obviously you can't because of the collisions. But there's got to be a way to send and receive. And, you know, he has this inventioneering perspective that he had trained in him from his mentor, Bill Lear, who got it from Thomas Edison of you run into problems, that's when you really dig in and you learn the technology and you look and see if you can find a solution. Well, he thinks of a solution so we can send at the same time. And the solution is, if you think of this side sending, the collision isn't getting rid of the data. It's still there. It's like all muffled up. It's like if you had one radio station and another radio station and you held them at your ears. It'd be all this chaos. And so that's what's happening. This data and this data are coming and they're getting all intertangled and it's chaos. If only you knew the data you needed to subtract from the chaos. Because if you subtracted the data that you don't want, what would you have? Just the data you want. But wait, we do know the data where we want to subtract because that's what's this side is sending the data it doesn't want. So he has the idea, what if we used something called a balance circuit on each side, and the balance circuit, it will monitor what this side's sending and will subtract all the data this side's sending from the received. So both could send at the same time with a balance circuit, and it would subtract the chaos from the side that it doesn't want, and you could send at the same time. And you would have full duplex, full gigabit speeds. So he starts telling that, hey, you know what? If we used a balance circuit, we could actually send and receive at the same time, and we would have gigabit speeds. And they're like, that's a bad idea. And I'll tell you why. Because balance circuits can't handle frequencies that fast. That won't work. And the committee meetings ended with no agreements. So they did not finish the standard. Everybody went home. Dr. Billings went home, and he started working on making one of these systems with a balanced circuit on either end, and he got it working. He could send and receive on either end of the network wire, and he could go gigabit speed, and it wouldn't have the collision issue. So the next IEEE meeting, he shows up, and he starts getting out the proof this works. And as he's getting it set up, he's trying to tell them, hey, look at this, I tried it. They were like, stop, that doesn't work. Like, you are clearly faking it, okay? And one of the engineers got up and said, you actually should listen to what he's saying, because what he's come up with is pretty ingenious. And this wasn't like this little engineer who just showed up. It was actually Ron Crane, who was the one who was the main engineer who invented Ethernet. And he was there saying, what Dr. Billings has got here, you should look at. That's a really good idea. So then they kind of had to let him present. And he presented, and he showed them, you can send it both directions at the same time if you use this system. And still, a lot of people were like, you have to be faking it. That's not real. And finally, this committee agreed to disagree. And when they finally finished, they got a standard out where they approved it. And it was a half and half standard. So they actually agreed to put out two because they couldn't agree. So the first one was going to be the half duplex version. Remember that? Where send, wait your turn, send, wait your turn. Half duplex, which means half the speed. Okay? Then the second standard would be the full duplex, if it even works. And some even called it the Billings version because they thought it was a flop. So they put out two standards, the half duplex and the full duplex standards for this networking system. And guess which one is pretty much used everywhere? Well, probably the faster one, right? If it actually works. And it turns out it does, and it works incredibly well. And that system would enable us to be able to get speeds faster and faster than what we had even dreamed of in the early days, at least some of us. But being able to take little nuggets of knowledge that he knew and then apply them to the problem, he was able to make a breakthrough that literally changed the world. So when you learn things in places like Science Live, listen up, put them in your little mental toolbox thing, because you never know when you'll run into a problem where you can use those to change the world. Thank you.
That story sounds very familiar to me.
It's a very familiar
Yeah.
story.
I'd like to show you a photograph of a mess.
Of a mess.
Yeah, would you like to see a mess? This is a photograph of a mess.
Okay.
A picture of the circuit board that I made to be able to demonstrate that this would actually work. Because when you're going to send first of all, going over all 4 pairs was insane. It was stupid because we'd been doing it for such a long time, very successfully. You didn't need to, but the committee voted. And after the committee voted, we're going to go over all 4 pairs. And we got to have full duplex. And I said, I'm sure we can do that. Now, we talked about a balun, but there's a thing here called a hybrid, a magnetic hybrid. It was a feature in the magnetics that would allow you to connect the transmit and receive signals from the computer and then subtract out what you were transmitting so you actually could hear it. And in the wire on the oscilloscope, it looked all messed up, but after it was cleaned up coming into the receive side, we had 40 dB separation. It was pretty amazing. But anyway, I wanted to prove it by building a circuit to show them that we could run at these speeds. So I built this board, and the board was a mess. It had all of these little wires that were just manually soldered in. It looked like a rat's nest, and it didn't work. At those speeds, if you just run the data around those wires, it just goes all out into radio waves and it's lost. But I knew it would work, and so instead we designed a circuit board with traces. Isn't real pretty, but it actually has the ability to see the circuit work. And I took that back to the next meeting, and people really still had a hard time believing it would work. And some guys said, well, maybe it worked 10 feet. At any rate, it did work, and we got a big controversy going. And Tobias was nice. They didn't call it the Billings method, they called it the Billings Folly.
They did.
And they said, if we make this, you won't be able to have a wire longer than 3 feet, if it works at all. And so I showed them how I could go 300 feet, which is the standard for Ethernet.
Yeah.
And anyway, well, to put this all into perspective, I'd like to see exactly what the proteges would say about it with the Inventioneers. Let's see them now.
Okay.
Today, we're looking at the first ever system that could stream video over the internet.
These days, we take streaming video for granted. We do it all the time. But believe it or not, there was a time where this was unheard of. Imagine you were a network manager in the 90s, named John. With this new Ethernet system, things would work quite well when you only had 1 or 2 people. But as you would add more and more people, you would start having collisions, which would sometimes take down the whole server. And don't even think about streaming video. And a lot of this frustration would be taken out on the network manager.
John, the server is down again.
Seriously, man, my fight is on. I can't log on. My file won't print. I've been waiting for 67 minutes and my file won't print.
I told you, I'm trying to make this work, okay? You gotta just give me a second.
John, I need my documents. I've been waiting over an hour for my documents. I can't log on. All this money is wasted. Oh my.
So you can see this was a pretty big problem. But about this time, someone... Did you hear that? At about this time, someone...
Okay, I heard it that time.
I don't know. At about this time, someone enters the scene. While working on his FSD invention, he encounters these problems with the collisions and how slow the network is. So he decides to Inventioneer a solution to these. And he decides to start a new company that will build these networking systems called wideband. Now, at the time, most systems ran at about 1 megabit a second. Some of the best cutting edge systems were around 10 megabits a second. But he decides he's gonna go for 1,000 megabits a second or 1 gigabit.
And on top of that, he wants to eliminate all collisions so that we don't even have to bother with them anymore.
And how he's gonna do this is he's gonna make a system with something called a concentrator. At the time, they usually had a hub in the center and there would be a wire running out to every computer. But if two computers tried sending something at the same time, they would just collide in the hub. So what if we replace that hub with something a little bit smarter, a concentrator? So then if two signals come at the same time, instead of them colliding, we'll just queue them up. We'll send one out first and then the other. So it's like cars in traffic. We can row them up and we can all send them out in order so that there are no more collisions. And if on top of that, you have things moving at a gigabit per second, you can really get things cooking. So he ends up getting this put together and people just did not believe him. They're like, with Cat5, the type of wire that everyone uses, if you send things that fast, the signal will just turn into a radio and fly off the wire because you're turning on and off so fast it turns into radio and just goes off into space. But he was able to make a system that would send gigabit over a wire. And so at one of their shows, they actually made this demonstration to prove that he was actually sending things at 1 gigabit per second. Let's go check it out.
All right, so this
Anyway, this is the actual demonstration that they took to a wideband show to prove that you could send gigabit over Cat5 cable. So this is where the internet comes in. It runs through all this cable and then it comes out through here where it's connected to our computer and we're streaming video over it.
Now, why did we do all of this? You see, at the time, the cutting edge biggest competitor for wideband was running at 10 megabit. This is running at a gigabit, which is 100 times faster than that 10 megabit. So the people from the 10 megabit needed something, so they would say, well, theirs runs at a gig, but it's not reliable over long distances. Like, you gotta use ours. Even though it's slower, it's reliable. And so we built this. They added all this extra cabling down here. They even added a nail through the Cat5 and then brought it up here, separated it into the 4 different strands and ran it across barbed wire, picked it back up into 4 strands and ran it output to here and still could run video.
And this is a good time to talk about something called half duplex and full duplex. Half duplex is what we've talked about, which is where you either send or you receive. You're never doing both at the same time. But because a Cat5 cable actually has all these separate pairs of wire inside of it, you can actually use one pair to send at the same time you're using a different pair to receive. And if you're doing that at the same time, that's called full duplex. And with the wideband system, it was doing just that. It was sending and receiving at the same time. And when they were showing this system off at shows, people couldn't believe it. They're like, you're faking it. You aren't actually sending stuff over that. So to prove that it was working, they would pinch the barbed wire together and short it out, which would make the video stop streaming. And you can see that's exactly what it's doing now. The other side of this was something called NIC cards, which would go inside the computer so that they were compatible with this system. Let's go take a look at those next. So this is what a wideband NIC card looks like. This is actually like the very first edition, and then he has a later edition. But you would need one of these inside your computer to be able to use the wideband services. And so then he was like, what if we could get these to come inside a computer by default? And to do that, you need a standard that everyone agrees on, so everyone is using the same technology.
So he's had this technology for a little while now, and a couple of years down the road in 1996, the Institute of Electrical and Electronics Engineers, or IEEE, is having a big meeting in Canada. So they're trying to make a standard for gigabit Ethernet. And so he goes to this meeting and he shows them, I have this working, like, let's just make it a standard. But they voted it down on the first day. Yeah. And what they wanted to do is basically go half duplex.
Yeah, they were like, since it's impossible to send gigabit Ethernet over pairs going this way and pairs going this way at the same time, we're gonna send it over all 4 pairs at once this direction and then all 4 pairs this direction. And the problem with that is you're gonna have all sorts of collisions anytime people are trying to send data at the same time. And it's like, there's not even a point to have gigabit. Like, we're going backwards in so many regards.
And so what does he do? He gets an idea. He decides he's gonna send gigabit over all 4 pairs at the same time. And he starts telling them this idea he has, and everyone's like, no way. So what does he do? He goes home and he builds a prototype and comes back and says, look. So what he's doing is he's sending data across those 4 pairs and the other 4 pairs at the same time and receiving it on both sides with no collisions.
Yeah, and basically how that works is because I know what I'm sending, I can get this garbled mess of what I'm sending and what I'm receiving. I can subtract out what I'm sending and just get the data that I'm receiving. And you're actually able to receive data where you're using the same pairs, sending both directions at the same time.
And he shows this off and it sparks a huge debate. There's 2 big factions and neither of them will budge. They're both like so set in their ways. Half of the people want half duplex and the other half are like, well, let's use this full duplex method.
Yeah, and the half duplex guys were like, that full duplex idea is so dumb. They even called it the Billings Folly. They were like, that's impossible.
So eventually someone has the idea, let's just pass 2 versions of it. We'll have one for the half duplex people and one for the full duplex people, or the Billings Folly. Fast forward to today, no one uses half duplex. Everyone is on full. It's much wiser and faster for Ethernet.
And as we all know, from there, the internet would get faster and faster to the point where now we have all of these crazy AI models and of course video streaming options. And now we can even watch things like Science Live.
You can even watch Science Live. So I have a question for you. Tell me what a NIC is.
A NIC is a network interface card.
So you remember there was one card, the first one, that was slow, and then we had this fast one for servers?
That's what I heard.
I remember it a little bit different. The first one was a NIC card made for an ISA computer, an old computer like an IBM PC. So that would plug into an IBM PC. But then they came out with the faster computers and they replaced the ISA bus because it was a bottleneck and put in the PCI bus. It was much, much faster. The other cards were for the newer computers. And one of them was made especially for a server because it had really big buffers in it. Okay, so now we've got something really interesting to hear about. This is one of the really big projects we've taken on here at IST. I'd like to turn some time over to Dr. John.
Well, I figured since we're talking about Ethernet, I should tell you the story about the 100 gigabit concentrator. This happened way back when 10 gig was, just starting to come out and wideband was doing really well, making these amazing networking products. And then the US Army needed really low latency networking. And remember, latency is how long it takes for the packet from the time it goes in to the concentrator to when it comes out. So that time, it's got to be really fast. And they wanted the really, really high speed, 100 gigabits. And so we told them, yeah, we can do that, really quick. And then I got the job to make it work. I was like, can we? Are you sure? And so then it was time to figure out how are we going to make this happen. And we still needed to have the transceivers and the FIFOs and everything like we had in the original concentrator. But in order for it to be fast enough and low enough latency, it needed to fit in one chip. So we decided to use an FPGA. This is a field programmable gate array. And if you compare this to a normal computer, like a CPU, then you can think of the CPU kind of like a chef. And so if you write a program, it's like the recipe for the chef, and the chef goes through each step in the recipe and they do it. Well, an FPGA is like
a whole bunch of chefs that do every step in the recipe all at the same time. And that's the difference with an FPGA. It does everything all at once. And so in order to develop for this, we had to come up with the design, of course. And then I wrote the whole design in Verilog. This is a programming language that's kind of like what you would use to write a normal program, except everything in the program is happening all at once. And so it's a completely different way of thinking about it. And then once the FPGA design was ready, we had to simulate it. And I want to show you a picture of a simulation. If you look at this, you can see all these little waveforms going up and down. That's the kind of thing you look at. These are the different digital signals. And you can see what's happening. And it's quite a trick to figure out exactly what is happening and then how to fix it and everything. So once it was working in the simulator, then it was time to place and route. And this is where the tools take the program and turn it into how it's going to hook up in the chip. And so if you look at all these little lines, those blue lines are the different wires inside of the chip connecting the different logic gates. And so this is how an FPGA works. And then once it was working there, we do the timing simulation, everything. And that takes a long time. Funny that that's the name. But then it was finally time to try it on the real hardware. I want to show you a picture of the real 100 gig concentrator. And that spiky thing, that's just the heatsink to keep it cool. But underneath that is the FPGA, and it has the transceivers, the FIFO, and all of the control logic in one chip. And that one chip has over 2,600 pins. That's 2,600 pins. This is a huge chip. And when we were designing it, the silicon didn't even exist that did what we wanted. And so that's why it was kind of a little bit of a leap of faith filling, you know, because we knew that it was coming. And so we designed everything in order to be able to have it ready in time. And then it was time to hook it up. And it was quite hard to get the program to load onto the FPGA. And I was working with Josh Merkley. He's our layout designer that made the PCB. And we're working on it, and fixing problem after problem. And this moment came where I realized, okay, it's going to work this next time. And so I pulled out my phone, and I filmed it. I want to show you what happened. So here we are. This is my computer. You can hear me there. There's the board, our prototype. It's loading on there. Wait a minute, it's taking too long.
I just started it too soon.
And so I turned back to the computer, and this is the program getting sent to the concentrator. You can see it running there. Ah, there it goes. And we come over here. Here it is. And then it didn't work. Oh, another time. So that was happening over and over and over again. But after I figured out what was wrong this time, I realized, okay, now it's going to work. And so I filmed it again. Let's watch that. Here we go. So there's Josh. There's the board.
It's loading.
Oh, it takes so long. And there it is.
It worked. And look, the lights blink. Success at last.
So you can't tell from that video just how excited I was. Finally worked. And instead of writing the whole big program that was going to do the really low latency 100 gigabits, it was just a little program that made the lights blink. You know, it's fun. But the reason why I did that was to validate the clocks. Well, you know, we have the clock signal coming into the chip, and then inside there's PLLs that change the clock frequencies, and it runs all over inside of the chip. And so this really simple program blinks the lights, and it blinks it nice and slow so I can time it and make sure the clocks are the right frequency. So it wasn't just for the holidays, you know, it had a real purpose. So this was a major milestone. And so then, of course, we loaded the real program on. This is the real moment of truth. And then in order to connect it, we had to plug in the cables. The cables look something like this. This is actually a fiber optic cable. And we stuck it in, and it didn't work. It's like every step of the way, right? And we had to debug the frequency, the signal in there, and luckily this chip had a built-in virtual oscilloscope to be able to see the signal. And so we could look on the computer and see the signal. This is what a perfect signal looks like, but ours was all garbled until we tuned it, and we got all the values set just right inside of the chip, and then it worked. And we were able to deliver it on time. And we had a challenge because it was so fast. How do you test the latency of something this fast? There's no obvious thing we could plug in and test it. So we used another concentrator, another board, and plugged it in. And so we would send a packet, and then we would time how long it took for the packet to come back. And we could calculate that the latency was way down there, just a matter of nanoseconds. Remember, a nanosecond is a billionth of a second. And a good way to think about it is the speed of light. The speed of light takes about in 1 second, it can go around the Earth 7.5 times. That's how fast it goes. Well, in 1 nanosecond, it goes about 1 foot. So that's how short we're talking about, really, really short. And with this speed, with our latency measuring tool, we could measure the latency of a cable. In fact, if you plugged in a 26-foot copper cable, then that is about how much latency our concentrator added. So it's like adding a cable is the difference. And so it worked amazingly well. And back then, 100 gig was brand new, and it was really, really fast. Nowadays, they're starting to talk about 300 terabits. Now wait, a terabit is 1,000 gigabits. So that's 300,000 gigabits. And the way they do this is with different colors of light over the same fiber. So maybe the next concentrator is going to be 300,000 gigabits. But that's all the tech we have the time for. Thank you.
Wow. The ISA card is one that is close to my heart because that one I did a lot of the work on personally. Now, other one I got some more help. But we manufactured tons of those and shipped them all over the world. And probably the most successful project I had ever been involved in financially. But when we got to the IEEE meeting, and we had a patent on this, we were going to give up the patent so they could use it royalty-free. They said no. And they said, we don't really believe that you can go reliably over the cable at that speed. The physics will not allow it. It's impossible. And they said, no.
They're obstinate.
And so it was that in that very first meeting, I made the presentation, they said, no. And they very quickly decided, we're going to send 1/4 of the data over each pair so we can send it at 1/4 of a gigabit on each pair. And
I can vouch for that. He did
that's
do that.
Though something that every Inventioneer needs to know about.
The frustration?
Politics.
Oh, politics.
It was a political decision.
It was.
And whether they made it because they really believed the physics wouldn't allow it, or whether they made it because they didn't want my company to get a head start, we'll never know.
I have my opinion, but.
Is anyone interested in her opinion? If you're interested in her opinion, send me a message. Okay. What do you say? What's your opinion?
I think they didn't want you to get a head start. Because there are a lot of big companies there that were
vying for that. I think some of
that.
them really, really thought it wouldn't work.
Oh, I know that's true.
I had a lot of problems, especially before I got it working.
Well, first when you brought
no one would believe it would work, and we started selling it, and boom, and it worked, and it worked very reliable. In fact, the old wideband equipment is actually more reliable than today's Ethernet equipment, and there's some reasons for that. But anyway, politics ruled the day, and the standard was we got to go this way. And I thought, if we bring out a product without it being full duplex, it's going to be a dog. And I didn't want a dog, and so I thought, well, it's got to go full duplex. If it has to go over all 4 pairs, And then I said, I wonder if we could send that through. And it's a really weird thing. When you even make a wave, like if you get a jump rope, you create a standing wave, or even with water, and you make a wave by dropping a rock in, and you drop another rock here, and the two waves hit each other. They go weird, they add and subtract, and then they come out normal again. And to think that you can do that with waves, it's funny. So you got this weird garbled wave, and when you get over here, you tune out with the hybrid. In the magnetics, mainly how it's done. The magnetics are the transformer that hooks the wire to your computer, but you cancel out the incoming signal, you cancel out your transmitted signal so you can hear the incoming signal, which is much weaker because it's come through the wire, it's been attenuated, the voltage is way down, but you can still pull out the data and you can do it reliably. And I was sure I could, but then I went and did it. And the first board, I couldn't get it through because it was a hair mess. But the second board did work, and we were able to reliably clock the data, and we went back, and Ron Crane and Ed Grivna from Cypress and John Marmon, the vice president of sales of 3Com, all of these guys came in and said, hey, this works. And because of all of the strong supporters, they did finally accept it in the standard. So now here we are, a couple years later,
yeah, a couple of
and
years
it has caught on. No one even, I don't know of anyone that sells the half duplex solution. And the interesting thing is, as time marches on, computers get faster, users start complaining, Gigabit is too slow.
Oh no.
It is too slow.
Oh, no.
So then they got another committee together and they developed the 10 gigabit standard, 10 times faster, 10 billion bits per second. And they used exactly the same method, bidirectional over copper for that standard. So now, remember, they say you can't send gigabit over one pair. Now they're sending 2.5 gigabit over each pair to get 10. So I guess it is possible. But it's fascinating. It's possible once you figure out how. And so often, the piece of the puzzle that you need to be able to do this is simple. You just got to figure out how. Now, Bill Lear taught me something, and he never told me if this is something he learned from Thomas Edison, but I assume it was, because Thomas Edison invented a lot of great tech. But he told me that there's a strategy of going after a problem. First of all, you really dig in and learn to know the problem. On the light bulb, the problem was it would burn out in just a few minutes. But he didn't see that as the only problem. He looked at it from a systems point of view. It burns out in a couple minutes, but where are you going to get the electricity? There's no electricity. And if you're going to make a commercial light bulb, you've got to have a way to have electricity there. And then third, when it does burn out, it's really hard to change it. It's all wired in. So he came out with a light bulb that would screw in and screw out. He had to get the filament lasting longer, so he went fishing.
That's right.
And learned how to make it last 1,000 hours. And now they last even longer than that. But when they did burn out, he could unscrew it. But then he came up with a generator to generate the electricity. And he went into New York City and he dug up the roads and he ran wires so that they could have electricity, and showed how the whole system would work together. That made him what I call a keynote inventor, because he put the whole system together so that people could really use it.
Keynote?
That's the second time she's corrected me on that. Who's the inventor here, anyway? What do you think it should be?
Keystone?
All right. From now on, guys, I know this is going to confuse you. We're going to call it a Keystone inventor.
Okay. Could be Keynote.
Yeah, no, it's Keynote. Keynote is something else, isn't it?
Yeah.
Keystone, when you're building an arch with rocks or blocks or bricks, and you get right up to the top, you put in the last stone, and you have to hold it up with some kind of wood structure or something until you get there. You put in the keystone.
Yeah.
And then you take it out, and the weight mashes down and crushes together and makes it very, very strong. You can drive cars across the top.
It's amazing, actually.
And Keynote, you can't do that.
Really? I didn't know that.
I'll explain to you after.
I remember standing there for that picture, the barbed wire picture.
Do you remember that?
Oh, yes. We used all that on wideband material.
Yeah. So she had a secret weapon. She would wear these white boots.
Yep.
And everybody come to find out about the white boots.
Do you know about Gigabit networking?
That's how she sold it. It's using your boots.
Yeah.
And by the way, she invented those boots, didn't you?
Yes, I designed them.
Yeah.
Oh, I
now,
invented them.
You guys that are being mentors, I'm going to give you a little heads up. When you're mentoring an Inventioneer and they come up with this harebrained idea like, I don't like boots. They don't look good. They don't feel good. They hurt your feet. They pinch your toes. Blah, 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 blah.
You mean somebody who complains?
You have to listen to them, and you have to encourage them. So I said, well, why don't you design your own?
True story.
I didn't realize what I was saying. So she comes back, and she holds up a piece of paper, and it's shaped like the toe of a boot. And she says, there it is. And I said, what is it, a mountain? She says, no. That's the way that a boot toe should be shaped. I said, says who? Says me, the designer of the new boot.
Yeah.
And so she sent that to the guys that build the boots, and they said, we don't have a, what do they call it, a model that fits that shape. And she says, so how are you going to get one? And so they did.
They did.
And she sold a lot of boots, and people love them because they are more comfortable.
It's all because I got challenged.
Okay. No, you got encouraged.
Oh.
I didn't challenge you, I encouraged you. I said, well, why don't you just design it?
Yourself.
And she did. Well, Gigabit networking, wideband, has been a really fun project for me.
Yes.
And we went to shows all over the world. We sold it in many, many countries. It was very, very successful. I feel like there's a key here that I would like to pass on to you, and that is the key that unlocks success for an Inventioneer. Find a problem. Now you say, one problem is we can't go to the sun. Solve that one. And like Tobias says, well, we'll go at night. That doesn't work. Some problems are beyond our reach. And believe me, I have a lot of projects in my mind that I want to finish as soon as I can figure out how to do them. My favorite on ice project is how do you store hydrogen safely, compact and lightweight inside an automobile? If someone solves that problem, it's going to completely change the automotive industry. And I worked on it. I've spent millions of dollars on that problem, and I've learned how to make it safe. I've lowered the pressure, and I got the cost down, but I'm still working on the weight. The tanks are still heavy, but they work. We put them in buses, put them in a mill jeep, put them in a lot of things. But I have come up with what I think is the minimum performance that the tank has to be at, and it has to store hydrogen at 4 weight percent. 4 weight percent means that if you have a tank that weighs 100 pounds, it has to be able to store 4 pounds of hydrogen. And the best reliable, safe tank we've been able to build so far can store 1.9 pounds. So it's got to get twice as good. Now, we have one tank we built that can store 7.2 pounds. But unfortunately, when you start pulling the hydrogen out, the tank gets cold and no more will come out, so you have to heat the tank, but you have to heat it enough to burn 1/3 of the hydrogen to get it out. So that didn't work. That is a breakthrough that I'm waiting for. I'm looking for it all the time. In fact, the other day when when AI came out, I said, how can I make a 4-way percent tech? And Grok said, I don't know.
Oh.
I'll ask you tomorrow. I believe it'll come. But the thing is, I know exactly what I need. So when there is a tech that can do that, that's affordable, that's safe, that can be manufactured in volume, it will completely change the automotive industry. But until it comes, we can sell maybe a few 100,000 cars in special situations, but that's the Achilles heel. It's the piece of the technology that's missing. If you're going to be a keynote, Keystone inventor, you have to have a whole system that works. And quite often you can get 80%, 90%, but until you have all the pieces, you don't really have a bridge you can drive over and have success. So as you're looking at these problems, you look at a problem, but then start figuring out ways that you can fix the problem. Step number 1, find a problem. Step number 2, figure out what's causing the problem. What is it about that is causing the problem? And then figure out a good solution. That's exactly how I approached education. I could see that some kids were not flourishing in their schooling, and I wanted to see if we could get education to stand up on its hind legs and succeed. And so as we got into education, we started finding a lot of things that were hindering different students, and then we started searching for ways of solving those problems. Eventually, we were able to come up with technologies like vectored instruction, etc., which have made a real big difference. So I'm encouraging you, especially right before the science fair, look for a problem, come up with an idea. Sometimes the simplest solutions in the world are worth a fortune, and they can make our world better.
That's what you're all about, isn't it?
And with that in mind, I'd like to show you my little friend that I keep in my lab. We got him back.
Ladies and gentlemen, boys and girls, welcome to Area 51 because we are doing science here, and it's the best science we've done forever. This is Science Day, and the big R says we need to learn how to make a network. We need to invent our own network. And just so that everybody knows what a network is, I'm going to explain to you. It's when I'm standing way over here and Lady Paget's way over there and she can't hear us. And so what we're going to do is we're going to send her information over the network we invent. And that's how networks work. They carry information from one person to another person. And I'm just going to show you how it works. First of all, we need to build our network. And I wanted a lot of big machines, but this is all the big R gave us. It's just this stuff here. So I'm going to have to take a picture of this. Now I'm going to upload this on the internet and ask, the intelligences if they can tell me how to make a network out of these things. Here we go. Oh, I know how to make the network. We're going to have to put this together. So you kids don't go to sleep. I'm going to kind of speed this up a little bit because it's going to take a lot of work. Okay, here we go. Here we go. Go! We're done. Lady Paget, we built a network so we can communicate with you. And I know you're so excited. So I'm going to turn on the network. Wait just a minute, watch. I'm going to turn on the power. This power is a little bit too short. So we're going to fix it. Yeah, don't you worry, Pichet. This network's going to work real good. We just need to make this one just a little bit longer. Yeah. There we go. Now, you can ask us a question, and we'll use this network to tell you the answer. Okay, do you get what we're doing here, Lady Paget? Okay, here we go. What is your first question?
Do you like gray?
And the network, I'm going to send you an answer. Here it comes. Now just watch. Here comes, Lady Paget. Can you see? The answer is no. It works. It worked. Let's do another one. Ask us another question. What's your other question?
Do you like green?
Do you like green? Right. Here comes the answer over the network. There it comes. Can you see, Lady Paget? We do like green. Isn't that just great? Okay, get ready for another set of big questions over the homemade network. Here we go. What's the next question?
What is your favorite color?
Well, our network's not supposed to answer that question.
Okay.
I guess. Our network is not supposed to answer that question. That's a good Inventioneer line, you know, and it doesn't work. It's not supposed to. Never intended it to do that.
Yeah.
Well, I hope you're really enjoying spring and you're getting ready for a wonderful science fair and you're getting ready for Celis World. We're looking forward to seeing a lot of you here, either virtually like R51 or in person like Lady Paget. But until then, remember, study hard. Everything you learn is going to change your life for the better. Thank you. We'll see you next time.